Now, I will switch to a PowerPoint. So I gave this presentation in a very interesting country called Latvia. So if you have no idea what is Latvia, Latvia. So that was my first time to Latvia because I have an international project with them and also with Lithuania. What is Lithuania? Litauen. Okay. So it's a 3-country project. So when I first went there, I was invited as a keynote speaker. I need to tell them where Taiwan is, otherwise they think we're Thailand. So that's what I did. And I think for you guys, you can use this opportunity to know where it is Latvia. So Taiwan is, like, size-wise, is around half of Latvia. What's interesting about Latvia is that they have no mountains. They have flat grounds, a lot of forests, no mountain. So our Latvian partners came to Taiwan this year as well after the COVID. They were so excited about mountains. They have never seen mountains for their life. So I think some of our partners went to the Elephant Mountain one day just to experience mountain climbing. For us, it's boring, right? Anyway, population-wise, Taiwan is 12 times larger than Latvia. We have 23 million, they only have 2 million. Taipei is 2.6 million. Taipei itself is having more people than entire Latvia. And I told them Taiwan is not Thailand. And by the way, anyone is from China? No? Okay, I told them we have fuzzy relationship with China. I told them about there's an election and then it's crazy. Anyway, starting my talk. I started my talk with this video. Let me tell you what this video is about. So it's an it's a National Science and Technology Council project. So in this project, we are supposed to, this is a student from Professor Cao Longyang in industry management. So we don't like to have boys as a model, just beautiful students. And the robot is picking up something, and the robot is supposed to drop the part in front of the student. And she intentionally moved her arm to a certain spot so that there could be collision. And from this video, you can tell the robot made a route surrounding the student's hand, because when it realized there is an obstacle, the student's arm was considered as the obstacle. When it realized that there is an obstacle, some calculation was done inside the computer, and then asked the robot to stop and move along a different trajectory. For the rest, it's just the other part of the project. Our partner analyzed human motion and realize what is the right moment for the robot to join this collaboration. But actually, to make sure this operation moves smoothly, we put some buttons here. Actually, we push the button so the robot knows when to come. But eventually, we don't want the buttons. We want this to be done with some kind of agreement. Whenever the human complete a task, computer should know. The robot will jump in and then do the next move. But right now it's very challenging. Okay. Anyway, let's see the obstacle avoidance again. So I will tell you when the robot realized there's an obstacle and then decided to move around the student's hand. When she moved her arm forward, look closely, the robot stopped for a very short time and then took a new route. Within that short period of time, all the calculations were done. So look carefully. Stopped. Right there it stopped. And then took a new route. It was not a smooth movement right there because it realized, oh, there's some obstacle. Okay? Like I said, within this research, there are 3 parts. The first part was done by myself and my students. We worked on path planning with obstacle avoidance. The other part was done by Professor Yang Caorong in industrial measurement. He used a camera to realize what the student is doing with human motion recognition. The third part is laser projection. It's by Zhang Jingyuan from Taipei Tech. He made one laser at the top. There is actually some laser indicating what the human worker needs to do, like a hint. But it was not clear in the video. If you are close by, you can see the laser. Okay. So anyway, this is what we have done. Later on, when you work on the project, if you are interested in this kind of topic, you can let me know. I can find my graduate student to jump in and then maybe show you what's available and what you can work on. So this is actually the exact procedure that I showed you earlier by the handwritten procedure, but this is more like a block diagram. So whenever you have a plan for motion, let's say moving from P0 to Pn, you need to detect whether there is obstacle. So usually you have some sensor or camera surrounding the working environment, like what I showed you in the video. There's actually a 3D camera recognizing the 3D coordinate of the student's arm. When the arm comes in, all the coordinates were captured and tell the system that along the trajectory there's this particular obstacle. So our system was basically doing exact calculation that I showed you. And once we compute every future configuration, because if you move up to a certain point, you don't need to worry about what's in the past. You just need to worry about what's in the future. So over here, the computer is calculating every possible configuration in the future and the shortest distance between the configuration and the obstacle to check whether it's safe. If yes, continue. If no, you need to use something to replace the trajectory. And this is exactly what I told you about the simplified model. Every body part has been simplified as a larger, fatter cylinder. It's easier for distance calculation. So in this animation, you probably can understand what this procedure is about even better. So from P0 to Pn, originally it was supposed to move in this way. However, while it's moving, there is an obstacle being detected. Then we check it's not safe. we realize within a certain region, every configuration within this region is not safe. So we choose this region as a obstacle avoidance region. We need to move, we need to find a safer route. So in this research, we need to find this new trajectory so that our robot can move like this. Okay? So let me tell you what people have done in this field. There is one way, so-called potential field method. All kinds of potential field. Basically, this algorithm not only can be used for robot planning, can also be used for like a vehicle positioning. Okay, it's very commonly used with this potential field method. Of course, the assumption is you need to know where are the obstacles. Those are obstacles, and you have a starting point. You have actually the starting point here. You have an end point. So you know all the coordinates. Now, most straightforward movement is to move straight, right? And as you can see, along this straight line, there's gonna be collision. So in computer, when we try to do this, we already know there is collision. And since we know about the coordinate of everything, they assign some kind of potential energy on those geometries. So they're like magnets. They have opposite magnetic field, magnetic force, pushing you away from the wall. So when you are about to move up to here, that magnetic field pushing you toward the other direction. So over here, computer figure out some kind of algorithm to realize you have to move along a different way. So not only they have this potential field pushing you away, they also have some kind of magnet from the target. So the magnet is pulling the starting point toward itself. So this is like a positive potential field, and the obstacle are like negative potential field. This pushes you away, the target pull you in. With the combination of all those magnetic fields, it determines where to make the turns. Okay? The issue of this method is that think about all these possible positions in the design space. Whenever you need to figure out where to make turns, in fact, you need to compute the shortest distance. The potential field, every potential field is computed based on that shortest distance. If you are closer to the obstacle, the magnetic field is going to be stronger. So if you move even closer, that you have even stronger potential field. So all these calculations is basically based on the shortest distance calculation. So since this method is exploring the entire design space, you can tell they have small arrows, they are magnetic fields. They basically study everywhere inside the space, and then they can freely move without collision. But that requires a lot of calculation. So a different way is called Dijkstra's algorithm. The Dijkstra's algorithm doesn't require you to move along the entire design space. It's a floor exploring algorithm. It's like pouring water from the entrance, and then the water started to explore until the water reaches, it's like a flooding, reaches to the target. Once it reaches the target, the computer will figure out, okay, how many steps it has been taken. There is one trajectory or multiple trajectories that took the shortest path. Then move along that path. Okay? The issue of this, what's the issue of this? Whenever you explore, again, you are checking every position, whether that position is safe or not. Whenever you are checking if it's safe or not, you are checking the shortest distance. So from here, every red point requires one time of shortest distance measure. That's also a lot of it. The next method is called the A-star. It's a improved Dijkstra method. So in A-star, they don't try to explore everywhere. So whenever they take a move, in this 2D space, you basically move forward or move left. They have some calculation to decide, okay, is forward better or left better? They will decide one. So they always move along one direction. Until up to here, moving this direction makes more sense because it's closer toward the target. But whenever it's bumping into an obstacle, then you need to explore more. You see, over here it's actually exploring more. Some extra exploring. Over here is more like an A-star, like a Dijkstra. But it doesn't overdo it. You only explore the space close to the possible path. And again, even you're doing this, you are still checking shortest distance. Okay. Now this is, from here, people started to try different ways. They try to use random procedure. So this is so-called a probable roll map, probabilistic roll map. What did they do? They basically assign random intermediate points in the space, just randomly assign them, and then try to connect the dots between, they try to connect the dots with straight lines. They don't connect the long ones, they just try to find the closer ones surrounding every point and then try to connect them. They don't connect the long ones. So whenever they connect those straight lines, they start to determine whether on a specific line collision is going to happen. So over here at the bottom, that yellow point is not a good point because that causes collision. So that one will be removed. Once you have some kind of network that allows you have a connection between the starting point and the end point with zero collision, then pick up the shortest distance. That's it. However, when you have that, the checking whether it's collision, you basically have distance measurement again. So if you need to do distance measurement along this path, that means you need to do that everywhere. On every connection, you need to do distance measurement. Still, it's a lot of calculation. Okay, so someone come up with this newer, more advanced approach, so-called the RRT, Rapid Exploring Random Tree. This method, the two most famous methods in path planning are A-star and RRT. A-star is easy, RRT, the procedure is more complex, but it's quite efficient. So they don't explore the entire space anymore. They start from the starting point, just explore your neighborhood. If there is a bad path, eliminate the bad one. Okay? And then you don't pick up the one that's over a certain limit. Like earlier, this one collides, even if it's inside a certain allowable region, but it collides with the obstacle. This one is eliminated. This one is outside. You don't want that. You just want to explore the neighborhood. So keep on doing that. You could have small branches until you reaches to certain area where a point is close to the target, within a certain range. Then you connect the target with at the end of the branch. So you find a trajectory, a complete trajectory. So researchers believe with this way, you don't need to explore too large a space. You can go through a smart trajectory. Then there's someone tried this a dual tree RT. Same idea, but they have two branches starting from both the starting point and the end point, like this. Okay, until both branches have single point closer to the other one, then they connect those two neighboring points so that they find a complete trajectory. They believe this dual tree RT allows you to explore lesser space. You don't want to explore the whole world, right? You just want to explore what's possible. Okay, now I would like to introduce what we did in our lab. There's a reason why we don't use A star or RT. A star is more like an exploring algorithm. It's like you don't need intelligence. You just need to explore. You just find a more effective way of exploring. And for the RT, it's based on random process. My research field is about optimization. We don't like random process. My advisor and my advisor's advisor, we never use random. We don't like to use random points. We would like to derive algorithms that helps you to find a solution. So if you want to know more about what I'm planning to do, you need to take my optimization course. If you have done, basically the difference is there is a bunch of algorithms that's based on so-called a gradient. The other ones are based on random process. We don't use random process. Only the weak students use random process, like a genetic algorithm. When you publish a paper, if you use genetic algorithm, the other group of people will think, this is nothing smart. So we want to develop something that's smarter. Okay, so in general, you are moving from, this is basically the P0 and that's the Pn. And it's a general configuration, so I use, the robot can have any shapes. So it's a general configuration. This is the jth body, right, like I said. And this is the coordinate of the n effector. X is representing the joints, a vector of joints, okay? Basically the configuration. So let's say there's an obstacle Q on the way. At a certain moment when your robot configuration is having the first contact, I'm calling this the first collision point. So F represents first collision. And the robot keeps moving until it reaches to certain configuration like this. And if this is the last configuration that has collision, the next moment it moves, the collision finishes. So I have a first point and a last point. So that I define this as a robot collision region. We want to avoid this part. However, if I move my robot up to here and start to make turns, you already have tangent contact. You don't want that. So in our research, we usually find a configuration a little bit earlier away from the collision. Because we already use first and last, so over here we use head and tail. So this is the head point to avoid the collision. And then we find a tail point This is the tail point, head and tail. So we define this region as the obstacle avoidance region. If we are able to find a trajectory that will not, that is away from the danger region, so we won't be able, we won't have contact, and also we can move around it. So let's focus on this collision avoidance region. Over here, we pick up some intermediate point here, some intermediate configuration. The idea is that we basically want to find a newer configuration from here to here. So here is not safe, here is safe. If you can choose multiple points here, then you can find multiple newer configuration on the above it. Then you can just connect them. So that was the idea. We focus on one configuration and find a safer one to replace it. Okay? So that's the goal. If you can find one, then you can find a lot of them, just connect them later on. So from now on, we are going to focus on just one configuration within this obstacle avoidance region. Now, here's the trick. We don't want to deal with n effector coordinate anymore. From now on, when I do any analysis or optimization, I stick with the configuration coordinate, basically a vector of joints. Why do I do that? Because I don't want to do kinematics anymore. If I use the n effector coordinate right here, then in the later analysis, I need to do inverse kinematics for x and then forward kinematics for p. I will need to do this back and forth for so many times. I don't want to do that. That is wasting some time. So let's focus on the design coordinate with x. If it works, I never need to do kinematics anymore. So the idea is I need to find a newer point right here to replace this one. But this one was a good one. The only bad thing about this one is that it will collide with the obstacle. The main reason is because it's not safe. But this particular point fulfill your objective, which is moving from the left to the right. So that was a good point. So the idea was I try to find a point that is as close as possible to this original point. I want to be closer to it because this was a good one. So I set up an equation that calculates the distance between two. Okay, remember that I want this to be small. It's okay to be small, but when I try to make this smaller, I want to keep my safety. So maybe when I reduce the distance up to here, it's already reaching my safety level. Then I don't shrink this distance anymore. Then I will be finding a safe point that is the closest to my original. So I will be moving just surrounding the obstacle, not like this. I don't want to do this. This is a solution, of course, but it's less efficient. You need to move with a longer time, waste a lot of energy. You want to do this, right? Just enough safety. This is too safe. Okay, now that is one. And we realize we also need to shorten this distance and this distance just to balance, make a good balance. These ways are very similar to the potential field method. They are like magnets. they have pulling forces. If I try to shrink all three directions, this point will be being pulled down toward the origin. Okay? So that was the idea. And basically, that's a lot of math, so don't worry about some of the math. Basically, over here, that's where it's dangerous. So we want to evaluate something called the danger factor. The danger factor is going to be calculated by the shortest distance. I want the danger factor to be small enough. If it's too high, we believe it's dangerous. So I will tell you about the danger factor. So exact analysis that I did, but this time I choose to use so-called the danger factor. There's a reason. Because robots may have large ones or small ones. For large ones, maybe you are in a different scale. The large ones could be 2 meters tall. Small one could be 50 centimeters tall. So when I apply a general method to robots with different shapes, I want a unified unit. I don't want the analysis to be affected by the size. So usually when this situation happens, sometimes we would like to normalize our values. We choose to define a new value called danger factor. Whenever the obstacle is right on top of the center axis of the cylinder, we say this is 100% dangerous. So danger factor equals to 1. Whenever the obstacle has tangent contact with the cylinder, even it's like this, or corner points, or on the side, whenever it's like a point connection, we say this is 50% dangerous. When it's away, 0 dangerous. So if we can model this danger level with values from 0 to 1, it's a unified number, no unit. It's just a percentage. So basically, exact same calculation, but over here we need to cut into 6 regions, unlike what I showed you earlier. Because we did some math to realize the danger factors has to be written in certain equations. It's more complex than the one I showed you. The handwritten one is a simplified version. This is a more because of the danger factor. Okay, so what's this? That's how the danger factor changes when the coordinate of the obstacle changes its coordinate. So I would like to show you what this means. So this is an exact drawing. If the center of obstacle is on this red line, danger factor has to be 1, right? So pay attention on the coordinates, the L. L is the axial direction of the cylinder. So L in this figure is right here. So here is L. So this edge is representing this red line. Okay, up to one half of LJ. This is 1/2 of LJ, right? Up to here, within this range. And R equals to 0. This is R equals to 0. So over here, this is like the obstacle staying on the central axis. And like I said, I want this danger factor to be 1. So these are danger factor equals to 1. Okay? And when the obstacle center is staying on top of the red dashed line, we will have point connection with the cylinder. So over here, I need a danger factor to be 0.5. This red dash trajectory is shown here. And take a look, it's 0.5. Okay? Now, when it's far away, I want the danger factor to be 0. And as you can see, when it's far away, it's 0. So we designed this danger factor within 6 different regions with those equations. So we try to make this danger factor as a smooth function. But it's not completely smooth because we have some corners right here. It's not good for derivative, I know, but it works okay. At least this function is well defined everywhere. So no matter your obstacle is inside the design space, no matter where your robot configuration is, you can find the RL coordinate of the obstacle and the jth cylinder, and then plug in one of the equations, then you know the danger factor. Okay, that's what was done. And then it's about optimization. So if you haven't taken my optimization, this is for your future. Take my optimization, then you know how to do it. So we want to minimize this distance, minimize this, and minimize this. ST means subject to. Subject to means 受限于. So basically limited by. Minimize these 3 things, but limited by those equations. One limitation, one constraint is your danger factor has to be smaller than an allowable value. If it's greater than 0.5, collision happens. You can set up as 0.4, so you will be keeping a safe distance away from the cylinder, because 0.5 is like a point contact. 0.4 is a little bit far away. So usually we use 0.4. And your angle, joint angle is limited by its largest angle and the smallest angle. Okay, and like I said, we formulate 3 equations. We want them serve like magnets, pull the design point closer to the original one, but keeping the safety level. So formulation-wise, I believe you can easily understand, but mathematically, you may not be able to understand. I'm going to show you, but don't worry, you just do not worry. There's something called Lagrangian. This is so-called the objective function, this is constraint function, this is actually one constraint function, the other one constraint functions. This is called the constraint optimization. It's difficult to solve for constraint optimization. It's easier to solve for unconstrained optimization. So there's one way to put constraint functions together with the objective function. It's so-called the Lagrangian. So it's like a weighted sum. Sum them up with some weights. Some weights. Those weights, 权重, are called the Lagrangian multiplier. You may heard of Lagrangian multiplier. What are they? They are the weights, 权重, in front of the constraint functions. So you just need to put them in the constraint with some weights. Okay? So this formulation is called the Lagrangian. But it's not easy to directly put them in the objective function. When you try to take a look at this, d minus d bar, forget about this, must be smaller than 0, right? But when you want to put this in Lagrangian, you need this to equals to 0. Cannot be smaller than or equals to. So we introduce a new variable. S squared is always positive or 0. So if this whole thing equals to 0, this value is either 0 or smaller than 0, right? So if this is 0 or smaller than 0, it's equivalent to its original equation. So we introduce something like this to make this equation equals to 0. This is only how you can put into Lagrangian. Whatever you put right here are called the slack variables. slack variables. Okay, I don't know why they do this. They're just names. Okay. If you don't know this, it's fine. I can give you the slides, but you can try. Once you have single objective function like this, then there is a famous method called Newton's method. Newton's method helps you to find the minimum. Okay? Whatever Newton's method you have learned probably is to find the root, 求根, like function, finding the root of the function, right? Usually Newton's method tells you where you have f equals to 0, right? But in optimization, we try to find where the derivative equals to 0. So Newton's method in your high school or undergrad teaches you how to find the root. But in optimization, it teaches you how to find the extreme point. And in our case, we are finding the minimum point. And it's a mess. This is so-called a gradient vector. Yes. This is a Hessian matrix. The gradient vector looks like this. Okay, if you're interested, you can take my optimization. And I'm gonna show you the Hessian. Looks like this. So just math, okay. Anyway, we can solve it. So the entire procedure looks like this. You want to move from A to B. You determine all the coordinates during the trajectory, during the path. You determine all the configurations. You check whether it's colliding. How do you check? You plug into the danger factor that we developed for every possible configuration. If yes, there's gonna be collision. Determine what is the first collision point and what is the last one. Then move wider, choose a head point and a tail point. That's where you want to do obstacle avoidance. Within this range, choose several more intermediate points. Solve for the optimization that I just showed you. And then you will have newer points, connect them. Then that's the avoiding trajectory. Now, time for animation. So here's one robot, and the red box is an obstacle. So originally, it is supposed to move like this, okay? From right to left. Along this path, this is the joint angle. I have drawn these figures for you earlier. Take a look. We have six joint angles. At the first point right there, the 6 axes are shown right here, different angles. Along the path, it's gonna move like these. Some are straight lines, some change a little bit, and some even move like a curve. Because when my student did it, I think he chose to move along the straight line. So if the end effector is moving along a straight line, you know the angle is gonna change like curves. However, we evaluate the danger factor. The red dashed line is the level of 0.5. As you know, 0.5 is collision. So the danger factor up to here becomes greater than 0.5, and then it's gonna collide, just like how we evaluated right there. So if we take a look at all intermediate points, we chose 3 of them. Now we want to perform optimization to find better intermediate points. So this is where we want to avoid. So focus on the first point. We use the optimization, Lagrangian formulation, Newton's method. During optimization, usually it's an iterative process, iterative. So the solution is gonna be moving around until it finds a good one. So I'm gonna show you the iteration. First iteration, second, third, Oh, that's optimal. We found optimal, a good solution right here, which is close to the original one, but keeping a safe distance. Okay? Let's take a look at the second intermediate point. Over here, it was colliding with the obstacle with optimization. First iteration, second, third, optimal. So we found optimal solution right here. Again, close to the original, keeping a safe distance. Okay. The third intermediate, first iteration, second, third, optimal. Okay, so that was purely done by math. We have no idea how. Basically, mathematically, Newton's method proved if you have that formulation, this is the solution. Okay? So overall, this was the original path. This is a newer path. So in fact, it moves like this. Just like how human would like to avoid the obstacle. And I'm showing you the dashed lines. The dashed lines are the improved ones. Over here, like this particular joint, black one is the sixth joint. It has to move along a new trajectory. And all these determined by Newton's method. And like the blue one is the third angle. It has to move like some new trajectory and determined by the algorithm. With the newer combination of the configuration, check out our danger factor. It's within 0.4. It has no chance to collide. Okay? And I'm showing you one animation. So the top one is basically exact problem that I showed you in the previous slide. The bottom video is a different path. So originally it is supposed to move from top straight down, but there's collision, so it made avoidance from the side. Okay, so this is with the first brand of robot. We did the same thing for a second brand of robot. Basically, this method is general enough. No matter what brand of robot you're using, it works. Okay, you just need to update the geometrical information. Okay. This is an interesting project. We work on an 8 degree of freedom robot. So usually a robot arm has 6 degrees of freedom, but this one has 8. We have a slider on this arm and this arm. So this robot is allowed to lengthen itself and then shorten itself. Why did the company do that? Because sometimes they have something in a shelf, they want to pick it up, but the length of the robot is not long enough. So sometimes they need to lengthen it. But they don't want the robot to be long all the time, because the walking space becomes too far away. Sometimes you cannot reach somewhere closer. So with the ability to change the length, sometimes you can reach closer, sometimes you can reach further. But when they design this, as you can see, you have greater degree of freedom. Now you have 8. You only need 6 degree of freedom. So you have 2 extra degree of freedom. So your possible solution become infinity. You have an infinite number of solutions for inverse kinematics. So usually for this kind of redundant degree of freedom robots, to find the possible configuration is more troublesome than 6 degree of freedom robot. Anyway, so what happened when we worked with them? They wanted to move from a point to a new point right there, and the joint 3 and joint 5 in this case, not 3 and 5. I think it's 3 and 1 of them. I don't remember which one. Ah, yes, 3 and 5. The joint 3 and 5 never changed. It's within this 0 area. So it moves just like a 6 degree of freedom robot. It never tries to lengthen itself. So from here you can tell, along the path, the danger factor reaches to very high. Some part of the body pass through the center of the box. So it's reaching close to 1. So we want to avoid those. Similarly, we use optimization to find a better point. And our method is general enough. We don't even care how many degrees of freedom we have. It's still being able to do this. So for iteration, first, second, third, fourth, fifth, sixth, seventh, optimal. So this is the optimal one. Second configuration, first iteration, second iteration, third. Okay, this is a fourth, optimal. Third configuration, first iteration. Oh, that was optimal. So the third configuration finds the optimal more quickly. So overall, it's moving like this. Combined together, this is the original trajectory, this is a newer trajectory. Oh. So what's interesting about this is that originally joint 3 and 5 doesn't change its length. This particular pink one is joint 5, basically one of the arm. The optimization asks this joint to change its length because it helps you to move around the object. So our optimization has no problem to modify the length. And the safety factor was kept within 0.4. This is another video to finalize what we did. So let's enjoy the video together. Exact execution that I showed you at the beginning. So that was the laser that I mentioned. So the laser is pointing at the position for screw. So maybe you have a mechanical part that is large, have so many screw holes, then the laser can help the worker to realize, okay, put the screw here and there. And that was the human body frame recognition. Okay. That's it for my presentation today. So I will share what I have, my slide on PowerPoint, on iPad, and also the PowerPoint I have. But I will remove the one with 8 degrees of freedom because I'm not allowed to put it on the internet. I'm not supposed to. Okay. Any questions so far? Do I need to assign homework? Do I need to assign homework? No? Not for this one, right? Do they need to write something about today's lecture? No? Up to me? Okay. Do you want to try to study path planning? But not the difficult ones. Try the simple ones. For example, this one. You know, this is done by Mela. This could be done by MATLAB. If you have just consider a 2D space. If you have a starting point and an end point, and you have some obstacle, you can have simpler obstacle like a circle. So if the circle is on the way, you are defining your intermediate point, you realize, oh, your n effector is too close to the circle, you can try to find a newer path. So in my slide, we have potential energy approach, Dijkstra, A star, random tree. They could be quite easily implemented in MATLAB. If you just stick with a 2D problem, simple circular obstacle, randomly pick starting point and end point. As whenever a straight line from the start to the end have contact with the circle, what to do. Okay? So I know you guys are in groups, right? Can we have a homework for today's lecture? You guys work in the group and you choose one way you would like and try to implement obstacle avoidance in any way. The goal is whenever, based on whatever assumption or setup you choose, but you need to be able to demonstrate a 2D space with some obstacle, circular obstacle with random position, random radius, and random starting and end point. Whenever the straight line has contact with the circle, what would be the path surrounding it? And if this has to be done automatically, then it requires some coding. Okay? Work with your team and see if you can implement it. If your team is cannot implement a MATLAB code, you want to try different codes, that's fine. If you just don't know what to do, you just want to, okay, can I just download something from the internet? Okay, that's fine. It's just a homework. But you will learn less if you just took something from the internet. And if you just, okay, even I download something, I have no idea what that code is. It never works. And you just want to study for some method and then give me a report. That's also fine. So I just want the team to focus on path planning, obstacle avoidance as a homework. You choose the level you want to hand in. Okay? The best would be, okay, let's focus on RT, a 2D problem, let's do some coding. Actually, it's not very hard if you do something like this. Random circle, random starting and end point, put in some random intermediate point, start to connect lines, check each line whether the line is overlapping with the circle. If it is, remove those. So at the end, you will end up with a network without collision. Pick up the shortest path. Nothing too difficult, right? It could be done within 2 weeks. Maybe 3 days from me. You guys can do it in 2 weeks. So how about handing in whatever you can get within 2 weeks? Okay. I don't want this to affect your project, but I think it will be a good start for you it could be guiding you towards something you want to do in the project. In the project, you want robot movement, right? And if you want to move, you don't want collision. So if this homework is going to help you on something you want to implement in the project, go ahead and do it. Okay? That's it for me today. Thank you. If you have questions, you can send me emails or talk to my TA. Talk to my student. They will they will let me know you have questions.
So we have to finish our homework group, but actually we have 2 types of group, one for case study, one for project. Which group?
Project group.
Project group.
Yeah, work with your project group. Yes.
Thank you.
Let me write down the homework so people are not confused. So, homework, work with project group, development of circle avoidance with random start and end points. Plus one circular obstacle. Okay, 2 weeks. If you, let's say 2 weeks later, you just want to do it, you just don't have enough time, I can give you 3 weeks. As long as you hand it in to me before the semester, I'm okay. I know if I do this, maybe our scoring needs to change a little bit, but the percentage of scoring remains the same. It just occupy some part of the homework. And I will give your team member the same score. I will not listen to whoever member complains he works more, I work less. I work more, he works less. So I get 10, you get 9. No, you are the same, you are a team. I give you the same score. If someone complains, okay, lesser teamwork, point reduction. So don't complain to me. You're supposed to work as a team. Your final production and how you work together is gonna be evaluated together as a whole. Your team get the same score as the homework assignment. I guess not too many points, just a few points. But I think this will be very interesting homework. Okay. Okay, thank you. I need to give you some time for the case study. I will give